My name is Philippos. Okay. Can you hear me now? Okay. Maybe not. No, I don't see any indication here.
All this wonderful technology and then.
Okay. Yeah, it's great. So, hello everyone. My name is Philippos. I'm a PhD student at the University of Crete in Greece. I'm also a member of the Computer Vision and Robotics Laboratory at the Foundation for Research and Technology, also in Greece. So, let's begin. First of all, let's see the problem. In this work, we're studying the problem of zero-shot object agnostic state classification. Now, object state classification has to do with the recognition of the states of object that appears in images. In our case, we study it under the zero-shot variation. That means that we do not use any training images as samples. And also, we have the object agnostic term. That means that we don't use any priors or any other cues regarding the object classes. Here you can see some examples. These are outcomes of our method. Now, why not follow the standard approach? That means to use a supervised classifier. If we do this, we have to find and collect the data, we have to annotate it, and then we have to train the classifier. This requires a lot of time. And also, all supervised classifiers are notoriously bad in generalizing across different datasets. So if we follow the zero-shot approach, there is no need to collect and annotate the data, and equally important, we will have a more robust classifier. Now, we need some auxiliary non-visual information, so we use knowledge graph to have this semantic information. But the problem with this is first that if we use some ready knowledge graphs, we will have a lot of noise, which is bad. And if we try to construct knowledge graph from scratch, this requires a lot of time and needs expertise. So this leads us to the main research question, namely, if by using large language model, we can overcome the previous shortcomings. So regarding the importance of the state classification problem, first of all, consider our everyday life. We interact constantly with objects, and we manipulate objects in order to change the environment around us. So typically, the functionality of an object depends on its state. Furthermore, state classification is very tightly coupled with action recognition, which is currently one of the most important problems in computer vision. And it could be said that the accurate state classification in many times is more crucial than accurate object classification. Moreover, it is a critical capacity for any planning agent, and it can be considered as another research problem. Now, let's see some special challenges posed by state classification. First of all, the accurate recognition of the state is very sensitive to minor details. Also, we have a great intra and inter-class variation. And a potential problem also is that the object class is much more visually salient than the state class. This makes very hard for a state classifier to learn the features that pertain to the state and not the object class. And finally, we have many object state combinations that are invalid. So let's proceed to the methodology. Here you can see the pipeline of our method. It consists of 5 discrete stages. What our method essentially does is to project semantic information into the visual space. And knowledge graphs constitute an integral part of our method. So now I'm going to explain each stage in more detail. Now, during stage 1, we want to construct a domain-specific knowledge graph. What we do is to build a knowledge graph around a concept, a set of selected concepts, which correspond to the nodes of the graph. So in order to construct a graph, we prompt a large language model and we pass the outcome. We use 2 popular LLMs, Llama 2 and Mistral 7 billion. And regarding the queried concept, we use the classes of ImageNet 1000 and Visual Genome, which are 2 very popular computer vision datasets. And also, we refine the outcome semantically using ORNet. And also, we use depth of augmentation. Finally, we also have experimented it with retrieval augmented generation. This means that before prompting the LLM, we give it as an input a text that is relevant to the problem in order to improve the outcome. And in this table, you can see the three different types of prompts that we used. The first is lexicographical. The second has to do with causal and spatial relation. And the third has to do with state-related facts. So the second stage. In this stage, we use the graph convolutional network, which takes as an input a knowledge graph and generate visual representation for each node of the graph. So in order to train this network, we have a subset of the nodes for which we know both semantic and visual representation. So we can see how far the visual predictions are from the ground truths. We have a loss, and then we can update the weights of the network. In order to have the visual representation for these nodes, we take a visual classifier, ResNet in our case, a convolutional neural network, and we extract its last layer. Now, during the third stage, now we want to construct a task-related knowledge graph that has to do with the target state classes we want to predict. So again, we go to the LLM, but now we perform queries or prompts related to these target classes. It's the same as the stage one. Now, during the fourth stage, we take the trained GCN from the second stage and the knowledge graph from the third stage. So now the GCN can generate visual representation for the target state classes. And for the final stage of our method, we take the visual classifier from the second stage and we replace its last layer with the visual representation of the fourth stage. And now our adapted classifier can predict object state classes. Now let's proceed with the experimental evaluation. First of all, we have conducted an ablation study in order to investigate several aspects of the problem, referring to the LLM type, the RAG, the semantic enrichment, the depth augmentation, and also the queried concept. As baseline, we used 30 different custom constructed knowledge graphs. In order to construct them, we query common sense sources such as ConceptNet and WordNet. And also we have compared the best ablated model against 5 state-of-the-art retrained visual language models. Now it is important to note here that although these models are considered zero-shot, they are not really zero-shot, and also they require a lot of time, computational power, time, and data. So as a classifier, as I have already mentioned, we used ResNet 101, pre-trained on ImageNet 1000. The metric that we use is mean average accuracy, standard metric in zero-shot recognition. And we have tested all methods in 4 datasets. You can see some details for these datasets. This is all the publicly available object states dataset. Now, you can see here the results for the method that use Mistral. The first column has to do with the queried concept, the second with the refinement, the third with the RAG, and the last 4 columns correspond to the 4 datasets. So we have 2 values in each cell. The first value is the mean value and the standard deviation for the 30 different knowledge graphs, the baseline. And the second value corresponds to the LLM-assisted method that we proposed. You can see here that in all 4 datasets, the LLM-assisted method achieves the best performance. Here you can see the results by using Llama and also by combining these 2 models. Again, the pattern is the same. That is, the LLM-assisted model is the best. So let's see some more interesting findings. We have observed that there is no significant difference between the models that are based on Mistral or Llama, and also that by combining these 2 models, we have inferior performance. This is suboptimal. Also that the enrichment of the knowledge graph improves in general the performance, but The depth of augmentation neither improves nor worsens the outcome. We have also performance gains if we use RAG. And finally, if we utilize classes from both the datasets, we have also higher performance. Now let's see the comparison with the other models. In this table, the first 3 rows are 3 different versions of our method. The first is the LLM-assist method. The second and the third are previous versions of our method. And the 5 last are the visual language models. Again, our method achieves the best performance. It clearly outperforms all the visual language models. I repeat here that this is not really zero-shot models. And also, we improve our previous baselines. So let's sum it all up. First of all, regarding the future work, we would like to experiment with multimodal knowledge graph. That means to include also visual and textual information on our knowledge graphs. Also, we would like to refine the prompting that we are doing. Right now, it's rather crude. So, for example, we could introduce some kind of a feedback mechanism. Also, we would like to utilize LLMs that support visual tasks. So consider that we give to the LLM images, and we have the outcomes for these images, a description of an image, for example, and something more technical. Hitherto, what we do is that we consider the knowledge graph to contain homogeneous information, which is wrong because the information that the knowledge graph typically contains is heterogeneous, sorry. So we would like to develop some techniques for this in order to exploit this heterogeneous information. Now, summarizing, in this work, we examine the interesting problem of zero-shot object agnostic state classification, and we propose a method that combines large language model, knowledge graphs, and graph convolutional networks. An integral part of our method is the utilization of large language models in the context of knowledge graph construction. Our method exhibits superior performance when compared against all competing methods. And finally, we consider that the combination of large language model and knowledge graphs holds more potential in the context of this problem. Thank you all, and I would be very glad to answer any of your questions.